We will now begin with section 3.7 and discuss the inverse of a function. We begin with the more general idea of the inverse of a relation. Recall that a relation is just a set of ordered pairs. So our definition says, let R be a relation. The inverse of R, denoted R to the -1, is the relation defined by R to the -1 is equal to the set of ordered pairs B, A, given that A, B is an element in the relation. What this is basically saying is that a relation is a set of ordered pairs, and the inverse of that relationship is the set of ordered pairs with the first and second coordinates exchanged. Let's look at an example to illustrate this idea. Determine the inverse of each of the following relations. Then graph each relation and its inverse, and determine the domain and the range of both. So our first example has the ordered pairs 4, -1, -3, 2, and 0, 5. So our first step is to determine the inverse of the relation. Again, the inverse of the relation is simply switching the x and y coordinates in each of the points. So our first point, which was 4, -1, now becomes -1, 4. Our second point, -3, 2, becomes 2, -3. And our third point, 0, 5, becomes 5, 0. And in doing so, we now have the inverse of our relation. It is also asking us to determine the domain and the range of both the original relation and the inverse. So let's look at this. If we look at the original relation, remember that the domain is the set of x values and the range is the set of y values. So the domain in the original relation would be 4, -3, and 0. Those would be our x values. Our y values would be the range. So -1, 2, and 5. Let's consider the domain and the range for the inverse. Again, the domain is the set of x values. So we have -1, 2, and 5. And for the range, we have the y values. So we have 4, -3, and 0. What you want to notice is that the domain of the original relation has now become the range of the inverse relation. And the domain of the inverse relation has now become the range of the original relation. So in other words, not only do we switch the first and second coordinates, but the domain and the range actually switch from one function to its inverse. Here's the graph of our original relation and also of our inverse relation. So the original relation had 3 points. It had this point, and this point. The inverse relation had 3 points. It had this point, and this point. It is important here to recognize that when you graph a function and also its inverse, you have symmetry across the diagonal line y is equal to x. So if I dot in this line right here, you can see that this point is symmetric to this point, that this point is symmetric with respect to this point, and then that those two line up. All right, let's look at our second example. Our second example asks us to find the relation y is equal to x squared, to find the inverse of that. All right, so this is part B. We have y is equal to x squared. So our original relation was y is equal to x squared, and we're being asked to find the inverse relation. And again, remember that what is happening when you go from a relation to its inverse is that you are switching out the x and y coordinates. You're switching out the x and y sets in the domain and the range. And so in your function, you can also write this as simply a switch between the x and the y. The y will become an x, the x will become a y, and now you have an inverse relation. All right, so let's talk about the domain and the range. And to do that, I'm going to go back and take a look at the graph of these two functions. All right, so this one is the original relation. This is y is equal to x squared. So let's talk about domain and range here. So the domain we know to be all real numbers, because we know that as these parabolas get higher and higher with the legs, that they're also going to slide over further to the right and over further to the left. And so the domain is going to be negative infinity to positive infinity. Or you could simply say the set of all real numbers. What about the range? We know that the range goes down as low as 0, but no lower. And then it continues up to infinity. And so our range goes from 0, including 0, to infinity. Now, this graph is the graph of the inverse relation. So this is the graph of x is equal to y squared. And so let's talk about the domain and the range for that one. So the domain, it starts at 0. We have nothing over here for our graph. So starting at 0, and the arrows indicate that it continues all the way to the right. So 0 to infinity. And then what about the range? The range is the height. So how far down does the graph go? How far up does it go? Well, it doesn't go up or down very fast, but as it continues to go out in towards the right, it's going to drop down or it's going to push up. And so our range will eventually become negative to positive infinity, or we could say the set of all real numbers. So again, notice that the same thing happened. The domain of the original function became the range of the inverse, and the domain of the inverse function became the range of the original function. So now let's move away from the relation idea and talk more about functions. So we want to introduce the horizontal line test. This says, let f be a function. We say that the graph of f passes the horizontal line test if every horizontal line in the plane intersects the graph no more than once. If f passes the horizontal line test, then f inverse is also a function. Okay, so this is very similar to our vertical line test that we use to determine if a graph is a function, but this time we're going to draw our lines across instead of up and down. A function f is 1 to 1 if for every pair of distinct elements x1 and x2 in the domain, we have f of x1 is not equal to f of x2. This means that every element of the range of f is paired with exactly one element of the domain of f. So let's simplify this just a little bit. All right, so what we are saying is that if we have a graph say we have the graph that looks like let's make it the x squared graph. Now we know that that graph is a function because it passes the vertical line test. So what I want to know now is, does it pass the horizontal line test? All right, so horizontal line test means that I'm going to draw a horizontal line and I only want to hit the graph in one spot. So since this crosses the graph in two places, it does not pass the horizontal line test. So I'm just going to make some notes here. So it does not pass the horizontal line test. So if it does not pass the horizontal line test, the function is not 1 to 1. And if the function is not 1 to 1, then the function does not have an inverse. And we want to keep in mind that an inverse is not always something that exists for every function. And so this is our progression. If it passes the horizontal line test, then it's 1 to 1, then it has an inverse. If it does not pass the horizontal line test, it's not 1 to 1, and it does not have an inverse. So let's look at a couple of examples. The first one says, determine if the following functions have inverse functions. All right, so we're going to do this by doing a graph of each of these functions. So we know that our absolute value function is the function that makes kind of a V shape with the vertex at the origin. So does this graph pass the horizontal line test? And you can easily say no, it does not, because the horizontal line crosses in more than one spot. Okay, so it does not pass the horizontal line test. Which remember means not 1 to 1, which remember means no inverse. So does the following function have an inverse? No, it does not. All right, let's look at this next one. G of x is equal to x plus 2 to the third. Okay, this is our cube function, and it's our cube function. What does the plus 2 do? It moves it 2 places to the left, right? So we're going to take that sort of S function, and we are going to draw it like that. All right, so let's check the horizontal line test. If I draw it here, I only cross the graph in one spot. If I draw it here, I only cross the graph in one spot. If I draw it here, I only cross the graph in one spot. So this does pass the horizontal line test. So what does that tell us? That tells us that this is a 1-to-1 function. So that tells us that the inverse does exist. Okay, so the last thing that we're going to work on here is we want to actually be able to find the inverse function for a given function, and this is a series of steps. So our first step in finding the inverse is to replace f of x in the definition of f with the y. Step 2 is to interchange the x and the y in the equation. Step 3 is to solve the new equation for y. And finally, put it back in function notation form by writing it f inverse of x. So let's try an example. Find the inverse of each of the following functions. And our first function is f of x is equal to x minus 1 cubed plus 2. So let's take that problem and follow our steps. So step 1 says to, instead of writing f of x, write it as y. So y is equal to x minus 1 to the third plus 2. Step 2 is to interchange the x and the y. So just switch their positions. So we'll write it x is equal to y minus 1 to the third plus 2. Our next step is to solve the equation for y. So get y by itself. So we can do that by subtracting this 2. So this will give us x minus 2 is equal to y minus 1 to the third. Solving for y, remember, the next step is going to be to take the cubed root of both sides of the expression. So we have the cubed root of x minus 2 is equal to y minus 1. And then our last step is to add the 1. So we have the cubed root of x minus 2 plus 1 is equal to y, which we'll then write in our function notation. F inverse of x is equal to the cubed root of x minus 2 plus 1. And we have our inverse function. All right, so let's try part B. We're going to do it the same way. We're going to set out, and instead of this g of x is equal to x minus 3 over 2x plus 1, instead of the g of x, we're going to write a y. So y is equal to x minus 3 over 2x plus 1. Second step is to switch the x and the y. So it'll become x is equal to y minus 3 over 2y plus 1. Then we need to start working at solving the equation for y. So the first part about this equation that makes it kind of difficult is that we have a fraction. So let's multiply both sides by 2y plus 1. And that will help us in that the fraction will go away on the right-hand side. On the left-hand side, I'm going to go ahead and distribute the x as I write it down. So x times 2y is going to be 2xy. X times 1 is going to be x. So we have 2xy plus x is equal to y minus 3. And our last step is to solve for y. Now the easiest way to solve this thing for y is to get everything on one side that has a y and get everything that doesn't have a y on the other side. So let's rearrange some things. I'm going to subtract this y off, which is going to give me 2xy minus y plus x is equal to negative 3. And then I'm going to subtract the x. So I now have 2xy minus y is equal to negative 3 minus x. So now we've separated everything that has a y from everything that doesn't. Next, we're going to actually come in and factor a y out of these two left-hand terms. So if I take a y out of a 2xy, that leaves me a 2x. I take a y out of a negative y, that leaves me a negative 1. So I have y times the quantity 2x minus 1 is equal to negative 3 minus x. Remember that you're solving for y. So we'll now divide by 2x minus 1. So I have y is equal to negative 3 minus x over 2x minus 1. And our last step is to change out the y for the function notation f inverse. So our inverse function is negative 3 minus x over 2x minus 1. The last comment that's made in this section talks about using the composition that we talked about in the last section to show that two functions are inverses. And so what it basically says is if you take your two functions and you compose them, f composed with f inverse and f inverse composed with f, that if the two functions are truly inverses of each other, you should get x in both cases. So real quick, we'll try an example. We're going to take two functions. I'm going to take f of x is equal to the cubed root of x plus 1. And I'm going to take a function g that is x cubed minus 1. And the question is going to ask, are f and g inverses? So in order to prove that, you have to prove two things. You have to first prove that f composed with g of x is equal to x. So let's do that first. So let's do f composed with g of x. We'll write our definition down, which is the f, and in parentheses we'll do the g of x. We will substitute in our g of x, which is x cubed minus 1. Then we will go to our f function and we'll evaluate at the cubed root minus 1, or x cubed minus 1. So I'm going to rewrite my f function. So the cubed root, when I get to this x, I'm going to put in x cubed minus 1, and then I have plus 1. So the 1's are going to cancel, leaving me the cubed root of x to the third, which is equal to x. So this part is good. Let's try it in the other direction, and you do need to show both ways. So we'll start with g composed with f. We'll write the g down and put the f of x in parentheses. So what is f of x equal to? F of x is equal to the cubed root of x plus 1. Now we'll go to our function g and we'll substitute in for x. So right off the bat we have an x, so we're going to write down the cubed root of x plus 1. That is supposed to be raised to the third power, and then minus 1. So this cubed root and this third power sort of cancel each other, leaving me just what's underneath, x plus 1. Then I have a minus 1, which gives me an x. If you show that both of those statements are true, then you can answer that yes, these two functions were inverses of each other.